Hi, welcome to video 4.2 4.3D. This is just more on properties of definite integrals and more areas. Okay, so we're going to look at that third property, the fact that the integral from a to b is equal to the integral from a to c plus the integral from c to b of the same thing, okay? We're going to take the first case, the most obvious case, which is if c is actually between a and b. For example, if you have 2 to 5, they're telling you you can break it up into 2 to 4 plus 4 to 5. Visually, of course, that makes perfect sense because the integral from a to b, for example, for this one is the green region, right? Bordered on the top by f of x, bottom by the x-axis. The blue region represents the integral from a to c, so as you can see, that's the blue region, and the red region is from c to b, so that's the red region. Well, obviously, the blue region plus the red region is going to equal the green region. I hope you're not colorblind. Okay. Now, let's take case 2. Let's say C is bigger than both A and B. Let's pretend A is less than B is less than C. So here, you can see it's actually still going to work. Because according to the theorem, the integral from A to B is equal to the integral from A to C plus the integral from C to B. You're just leaving the first one here and the last one there, and you're just putting this guy in between. So the green area would be the A to B. The blue area would be A to C. And the red area would be from C to B. Now, the thing is, though, because this is from C to B, which is going backwards, this would actually have a negative value, right? Because the dx's are all going to be negative, although the f of x's will be positive. So what I'm going to do is I'm going to switch the order, which is C to B. I'm going to switch that from B to C, meaning I have to change that to a negative. Remember that property? If you switch the order of the limits of integration, you have to change that to a negative. And now visually, if you look at it, isn't the green equal to the blue minus the red? If I took the blue region and cut out the red region, I'd be left with the green region. So it actually still works. So if you have 3 to 7, so far we've seen you can break it up into 3 to 4 plus 4 to 7. We just saw the third one actually. You can break it up into 3 to 9 plus 9 to 7. And now we're going to show the last one, which is what if C is smaller than A is smaller than B. So again, if I use the formula that they say, the integral from A to B equals the integral from A to C plus the integral from C to B. The integral from A to B, as you can tell, is this green region. The integral from A to C is this pink region. However, because I'm going from A backwards to C, right, A to C, the dx's will be negative. So the value of this will end up being negative. So if I want it to be positive, all I got to do is change the limits of integration. Instead of A to C, I make it C to A, and I can stick a minus out in front of that. And then the integral from C to B, which is from left to right, is this blue region. Well, sure enough, if I take negative the pink region plus the blue region, i.e. if I take the blue region and take away, subtract the pink region, I sure enough will be left with the green region. Okay, this is a typical AP question. Determine which value best approximates the definite integral. Make your selection on the basis of a sketch. Now, the point is, if you had a calculator or even without a calculator, you could actually figure out what this is exactly equal to, but that's not the question. They want to know what it approximates to. In the real deal, they won't give you the function. They'll just give you a picture of the function, okay? Now, what they mean by a sketch, well, of course, here's y equals cosine x. You know that. You should remember from from Algebra 2 and Pre-Calc, that the 4 represents the amplitude of the function, so it's going to go up to 4 and down to negative 4. The period is 2 pi, the normal period for cosine, divided by this multiplier on the angle, which means the period is 2. So it turns out that this function has a period of 2. Break that up into 4 equal parts, and it goes up to 4. So it starts up here, then it goes down to through here at a half, reaches its min at 1, back, etc. So we're looking at this red region, 0 to 1/2, bounded on the top by the curve 4 equals cosine pi x, and on the bottom by the x-axis. What they want you to do is not evaluate that integral, but look at it and go, oh, look at this rectangle. This rectangle right here is a rectangle that has a width of a half and a height of 4. Well, that means its area is 2. A half times 4. If you drew the diagonal, you could see that half of the area of that rectangle would be 1. And our region, our red region, is a tiny bit more than that half rectangle. So our answer should be a little bit more than 1. Notice the answers: 4, 1 1/3, 16, 6.28, and -6. It would have to be answer B. Sketch the region whose area is given by the definite integral. And again, we're back to using a geometric formula. So I just want to look at a few more of these. That's from another video anyways. But it's in terms of x: left border x equals 0, right border x equals 4, top border f of x equals x over 2, bottom border x-axis. If you draw that, you'll end up with a right triangle, and therefore the area is 1/2 leg times leg, or base times height, which, as you can see, is 1/2 4 times 2. And the reason I know that's 2 is because the right border is x equals 4, and x equals 4 intersects this line. You just replace x by 4. You get 4 over 2 is 2. So the height is 2, and therefore that is what that integral is exactly equal to. Here's another one. Left border x equals 0, right border x equals 8. The top border is y equals 8 minus x, which actually has a y-intercept of 0, 8, and x-intercept of 8, 0. So there's your left and right borders, your top border, your bottom border is the x-axis. Again, another right triangle. Again, 1/2 leg times leg. And that's the end of video 4.2, 4.3D.